Okay, in this video, I'm going to continue my discussion of confirmatory factor analysis using the Lavaan package written for R in order to carry out structural equation modeling. So in my previous video, I used the CFA function, and I went through a number of different models to show you how you can structure, how to structure your syntax when you are using Lavaan. Basically we're using the CFA package, and there are certain defaults associated with the package that you may not necessarily want to have when you are specifying your model, and you may want to have a little bit more control over what you're including. So in that case, you might choose to use the Lavaan function instead of the CFA function. So that's basically the emphasis within this particular demonstration here. So what I have right here, this is an open notepad, and I'm going to walk through this notepad to demonstrate the Lavaan function. And I will include a copy of this under the video description where you can download it. So first off, let me note that you can obtain information on Lavaan. First off, there's a basic manual found at this site right here. The demonstration from this video is actually associated with the article right here, and you can download a copy of that article from this link right here. And just keep in mind, this is a really good article. If you're learning about Lavaan, you'll definitely want to read it. It's very nicely written and has a very nice logical flow. So I'm just going to give the author a thumbs up on that one. Then we also have another tutorial site right here, so you can get that information. In addition to demonstrating Lavaan, I am also going to use semPlot package in order to generate a diagram of the model that we are running here. So if you want to know more about semPlot, you can go to this link right here. So let me just kind of say again that we are pivoting off of this article right here. It appears in Journal of Statistical Software, and more specifically, we're going to go down and I'll show you the demonstration is basically this one right here, looking at method 2 using the Lavaan function. So the basic model is going to be exactly the same as what's presented in the article. But again, I'm going to kind of walk you through each of the little pieces, and then also show you the semPlot, use the semPlot package in order to obtain a diagram for the model. Note that if you haven't already installed Lavaan, you'll want to do that using the install packages function. So you can see right here I've got Lavaan in quotation marks, and I'm also, if you haven't installed semPlot, you'll want to do that as well. So it's sem with a capital P right there, and then the remainder. So it is case sensitive, so be sure that you have factored that in when you are typing in those package names. Once the package is installed, we're going to use the library function in order to call up the packages. So R is not going to be able to do anything with the functions associated with those packages unless you call it up. So we're going to use the library function to do that. So the first thing that I'm going to do then is open up R, and I'm just going to go ahead and call it up. So I'm going to say library and then Lavaan. So this is going to open up the package, and then I'm also going to do library sem capital P and then plot there. And so that package is being called up as well. In my previous video, I demonstrated how to obtain the data. The data is actually this right here, Halsing or Swineford, 1939. And actually, Lavaan includes this data set. And so we don't actually have to download it or anything like that. It's already built into the program, and it will recognize this data frame automatically. But in my previous video, I also tried to show you how to read data into R before you actually carry out the analyses. So basically, we created a new data frame that was called this, and after reading in data from a CSV file. But in this case, we're not going to bother with that. We're just going to use this particular default data frame. So I'll show you what it looks like though. I'm going to copy it and paste it in here and hit enter. And this is the data frame. So you can see it's containing data and various minimal abilities for school kids. And you can see that we have X1, X2, X3, X4, X5. Then all the way up through basically X9. If we want to look at the structure of the data frame, we can also type in str and the name of the frame, and then there you go. So the indicator variables within this CFA model are appearing right here. So there's X1 all the way through X9. Okay, so let's look at the CFA model and the syntax in particular. So I'm going to move this. Basically, what we're going to do is we're going to look at. You'll notice that right here we have h.model.full, and this is actually going to be a name of a data object that's going to contain the model information. So we have to actually specify our model in order to analyze the model. So this right here is a data frame, and the model information is contained after, basically we have an arrow pointing to it, which is just a less than sign and then a dash. Then we have an apostrophe right here that starts the indication of our model, and then it proceeds all the way down to the end of down here where you see an end apostrophe. So all the model information is contained within this area right here. And so you have to start with an apostrophe, and then you have to end with an apostrophe, so down here. And the first line, you'll see it says there's a pound sign and then latent variables. And basically the pound sign is denoting that anything that follows on that line is a comment. So basically the program is not going to read anything with this. It's just recognizing that this is a comment. On the next line, we have visual, and that is the first factor in the model. So that's followed by equal sign and then a tilde sign. And then you'll notice right here we've got 1 star x1. So the x1 through x9, those are actual variable names in the data set. The 1 times, or the 1 star, is basically setting the factor loading for that first indicator variable to 1. So for the visual factor. If we wanted to use a different indicator, then we could have, let's say we wanted to do it for 2, then we would just remove that and just say 1 star 2, and then that would work just the same, except that 2 would be the reference variable instead of 1. I'm going to go ahead and keep this consistent with the presentation in the article, but that's what that is. You'll notice that we also have plus signs that are separating the variables as well. So visual, basically this right here indicates that visual is being manifested or indicated by x1 through x3. Textual right here is basically being manifested by variables x4 through x6, and then speed being manifested or indicated by x7 through x9. You'll notice that there's a pound sign. This is another comment line right here. So everything right here is a comment. And then you'll see this it says residual variances for the observed variables. So basically, by default, when you're using the CFA function, the residual variances are estimated by default. In this case, when using Lavaan, we actually have to specify that we want to estimate the residual variances. So here we have basically x1 and then 2 tilde signs and then x1. So basically this is indicating the variance for x1. Then for x2, the same goes as well. So there's x2 right there. The same for x3 all the way through x9. So we have to estimate it for the variance of the residuals or the errors for each of our indicator variables. Next, we have a pound sign down here followed by factor variances. And then we have visual and 2 tilde signs in visual. So basically this is estimating the variance for the visual factor. Then we have the variance for the textual factor, and then we have the variance for speed factor. Down below we have a pound sign. Again, we have a comment line for factor covariances. So for this, basically, we have visual, and then 2 tildes, and then textual plus speed. So basically, this is going to give us the correlation between visual and textual and speed. Then we have textual, 2 tilde signs, and then speed. So that's going to get us the correlation between, or the covariance between the textual factor and the speed factor. And then again, we're ending it with the apostrophe. So again, all of this information, this is the model information, and it's basically contained in our hs.model.full data object. So after we've specified the model, then we want to fit the model. So we're creating here a new object called fit, and the actual SEM that's being carried out is basically the information is going to be housed under that data object that's called fit. So you can see right here we have the Lavaan function, and then following inside the parentheses we've got hs.model.full. So that is the name of our basically our model up here. So this is instructing Lavaan to carry out our analysis of the model, where the next thing that we have is data. That's our data argument, data equals, and then the name of the data frame that we're working with, which is our Hausinger-Swinford 1939. So basically, then following, I've got some additional syntax that I've written in order to further kind of look at the data. So I've got, first off, I've got the summary function right here, and you'll see that inside the parenthesis I've got fit, and that the fit is the name of the data object that contains our analysis results, and then comma, and then fit.measures, I've set that equal to true. And then underneath I've got parameter estimates with capital E, and then I've got fit, that's our data object containing the results, and then standardized equals true. And this is going to give me standardized coefficients within the model. And then the last one, SEM paths, is essentially the function that's associated with the semPlots package. And so you can see right here we've got fit right here, and then I've got what right here equals quotation marks paths, unquotation marks, and then I've got what labels equals, and then quotation marks with PAR inside, and that's to basically get our diagram that includes the parameter estimates. So I'm going to highlight all of this and copy it and then paste it in R. And one thing that I want to mention is that it's really probably good practice to get used to typing up, particularly when you're working with more complex models or typing it up into a notepad or something like that, and then pasting it into R, because it's very easy as you're typing all this stuff in to make errors. And so just to avoid a number of errors popping up all the time and getting frustrated with that, if you type it out ahead of time, it'll make life a little bit easier for you. So I'm going to paste this in, and so now we see our output. So you can see right here, first off, that SEM paths right here, and once I hit enter on that, this diagram comes up, and so you can see that we've got the parameter estimates for each of the latent variables. The double-headed arrows are the variances for the latent variables. These are the covariances between the latent variables. You can see the paths that were fixed to 1 right there to scale the latent variables, and the remainder are the unstandardized loadings. Just so you know, too, if you wanted the standardized output, we could do that just as easily. Instead of using PAR, I'm going to type in, actually I'm going to copy and paste that in, and then type in quotation marks STAND in quotes, and then in parenthesis. And so then I get standardized estimates. And so with standardized estimates, you can see the variances for the latent variables are all 1. And then what you have are the correlations between the latent variables, and then we have the standardized loadings and so forth. So at any rate, as you're kind of looking at our output, let's kind of scroll back up and just take a look. So I kind of ran this as a batch, and you can see that in terms of the output, basically because under summary, I included fit.measures equals true. I get more fit indices than I would have gotten if I just said summary fit. So in particular, just kind of notice that I get the chi-square value. There's the degrees of freedom for the model. Statistical significance, our p-value. You can see that we get the CFI and TLI. Both of these are presented over here. If we scroll down, you can see that we get, like I said, a number of different indices. There's the RMSEA right there, 90% confidence interval right here, and then the p-close or p-test for close fit right here, and then we have the SRMR that's presented right here. So when you ask for the fit measures, when you set fit measures, fit.measures equals true, you're going to get all these. Otherwise, you just kind of end up with a very small subset, like the chi-square test. So if we look at under latent variables, you can see right here we have our estimates. So these are the unstandardized factor loadings, and you can see that the paths that were fixed to 1, these are them right here. So you can see there are no test statistics associated with any of those. The remaining loadings are given right here and right here and right here, and so they're also tested for statistical significance. If we scroll down and look at the covariances, you can see the visual and textual right here. So visual, textual, this is the covariance, and you've got the significance test associated with it. Visual and speed, there's our estimate and our test results, and then textual and speed right here. So all those are given. And then if we scroll down a little bit further, you can see that we get the variances for our indicator variables. So all these were estimated. You have significance tests associated with those. And then the variances for the latent variables that are given right here. When we had asked for parameter estimates right here, and then said standardized equals true, you'll notice that basically what we end up with under the EST column, these are again the unstandardized estimates. There's our standard errors and z-values and p-values. You'll notice that we get confidence intervals right here, and then you'll notice that there's a STD latent variable. These are standardized estimates, assuming basically that the latent variable is standardized. Generally, if we want to look at the standardized estimates, we'll want to look under the STD.all column. And so basically, these are pretty much what you would want to focus on reporting if you're reporting on the standardized estimates. So that pretty well concludes this demonstration. And like I said, I will incorporate this CFA model underneath the video description, this particular text file underneath the video description for you to download if you want to follow along a little bit more closely. But again, I do recommend going to some of these other sites. They're really nice documentation on the program, and it's a pretty nifty program. So I hope that you found this useful.